Okay, we're starting chapter 6. So far we have talked about differentiation. So derivatives of a function, but now we're going to do backwards. So far we have been doing is from f of x, we take derivatives, we arrive at the derivative of the function, the rate of change of the function. Now we're going to go backwards, so which is called anti-differentiation. So we're going to be given a function which is a derivative of some function. And we're going to call this capital letter F. Now we're going to call this F. So the lowercase f represents the derivative of the capital letter F. So that's going to be our notation. So when we take derivative, remember, let's give an example. If I have x squared, right, when I take a derivative, I get 2x. So we apply power rule. We take down the exponent, we move to be the coefficient of x, then we subtract 1 from the coefficient from the exponent. So to arrive at 2x. Now let's do the other way around. Now let's see we're given this function. And this function is some function is a derivative. So let's see we're given this as 2x. So how do we recover f? So we want to recover the original function or potential function. So we're going to do the opposite. So before we subtract 1 from the exponent, right? What we do is we take down this 2 to multiply this 2, then we subtract 1 from the exponent. Now we're going to add 1. So f of x equals to, first let's rewrite the function. Well, by default, that's 1, exponent is 1. So we're going to add 1, right, before we're subtracting. Now we're adding, we're doing backwards. So before subtracting, when we differentiate, now anti-differentiate, we're going to add 1. Now 1 plus 1 is 2. So we're going to divide it by 1 plus 1. So we'll add 1 to the exponent, we get a new exponent. Right? Add 1 to the exponent, whatever this is. Then we just divide by this new exponent. Well, let's simplify it. So we got 2x squared divided by 2, which is exactly x squared. But now, let's say another function. Let's say I have f of x equals to x squared plus 2. So when I differentiate f prime of x also equals to 2x, because the derivative of 2 is 0. So now the derivative, you see this function and both functions have the same derivative, right? This function, x squared plus 2, and this is x squared, or for any function, f of x equals to x squared plus any number, the derivative will be the same. So what do we do then? So when we do anti-differentiation, we're going to add a constant. We have no idea what this constant is because there's no information until we're given initial condition. If we're given the initial condition, we are given a point for it, we can recover this c. But for now, we just add a constant, we just add c to it. So that's it. That's anti-differentiation for polynomial-like. So what do? We add 1 to the exponent, we divide by the new exponent. Then we plus c. All right. For exponential function, it's a little bit different, but we're going to do exactly the same process. Okay, let's go to the textbook. So which is called anti-differentiation. Anti-differentiation. Okay, we're going to be given f of x, and we're treating as some function's derivative. And we want to be able to find the original function or potential function. Why potential? Because of this at c. But potentially c can be any number. So let's see this example. Determine the height of a rocket from its velocity. Remember, velocity is the derivative of the placement, right? Or the position. So that's velocity. So let's see. A rocket is fired vertically into the air. Its velocity at t seconds after liftoff is given this. So this is s prime of t equals 6t plus 0.5. So velocity is a derivative of the placement function. Meters per second. Before launch, the top of the rocket is 8 meters above the launch pad. So that gives us a initial condition. That gives us a condition C. Find the height of the rocket measured from the top of the rocket to the launch pad at time t. All right. So given the derivative function, and we need to find recover to the original function by using the information given. So basically, we need to anti-differentiate. So if S of t denotes the height of the rocket at time t, then S prime of t is the rate of change or the velocity. The height is changing. That is, S prime of t equals to velocity of t. So we do not have this yet, but we do know the velocity. So we can recover from here. Or let's try it. Remember, so S of t equals to, we anti-differentiate v of t. So we have 6t, let's anti-differentiate this one first. Well, originally that's 1, so we plus 1 to the default exponent 1. Then we divide by 1 plus 1, whatever the new exponent is. Then plus 0.5 t, right? When we differentiate 0.5 t, when we do differentiate, we get 0.5. So for this one, we just add t. Then plus some constant. Because when we differentiate any constant, that becomes 0. So now let's simplify this. So we have 6 divided by 2, which is 3, t squared plus 0.5t plus c. And how do we know c? C is given in the original one. It's in the top of pad is 8. So c is given initial condition 8. Initial means when t is 0. Right, t is 0 is 8. So that's why c is just 8. So this is our position function. It's a quadratic function or polynomial degree 2, right? Because its derivative is a linear function, polynomial of degree 1. So the original function increased by 1 degree. So that's the definition, right? Which is called f of x is an antiderivative of lowercase f. Let's see this one. So we want to anti-differentiate f of x equals x squared. So this equals to f prime of x, and we want to find f of x. F of x. Right? So we just follow the steps. So this is polynomial like. We have x squared. I'm going to choose a different color. I'm going to add 1 to the exponent. I divided by the new exponent. Then I add a c to it. Let's simplify this. So 2 plus 1 is 3, right? X cubed divided by 3, then plus c. So we can check if we take a derivative of this, if we take derivative of f prime of x, that would be 3 times x squared, right? That's x cubed. We'll differentiate x cubed, get 3x squared. Then we divide by 3. Then c differentiate, c is 0. So that's just x squared. So we did it right. So if we know the initial value is 5, right? So we have to add a c to it. But if we know the initial 5, we just add 5. But we don't know, so we just add c. Let's see this one. We want to anti-differentiate e to the negative 2x. So remember this. Remember we have f prime of x equals to m f of x, right? What is this m? M is a derivative of the exponent. M is a derivative of the exponent. So what is this? That's negative 2, right? So when we differentiate the negative 2x, we get a negative 2. Think about if we differentiate negative e to the negative 2x, we would get negative 2 e to the negative 2x. Right? This is the original function. So that's multiplying by it. So for us, we need to divide it by it. Well, this is saying f of x original function equals to derivative divided by such m. In this case, we see m equals negative 2. So f of x, again, we use this notation because this is f prime of x. F of x equals to e to the negative 2x divided by m, which is negative 2, because the derivative of negative 2x is negative 2. So we can rewrite, of course, we need to add c to it. So we can write as negative half e to the negative 2x plus c. All right. You may go through the textbook. Right, so the potential functions are family of functions, really depends on the constant term c. Now, we define something called integral. Integral. So the integral is this, is defined as such. So we want to so in this case, so f prime of x equals to f of x. Okay, that's a relationship. So the derivative of f, the capital letter F, is the lowercase f. And what is this? This is, you think about letter S, right? You elongate this S. You write this S, you stretch this S to be this sign. So this is called an integral sign. Where does this come from? We know the summation sign, right? Summation sign means adds up things. Right, let's see. Usually we do, let's give an example from 1, I want to add from 1 to 5, I. So this means add 1, 2, 3, 4, 5. So that's what this means. This is summation sign, big sigma. Okay. So this is a finite number. So when we do, if we take this one, I equals 1, let's say adds up to n. Now we take a limit that n runs to infinity. So this sign becomes something like this, 1 to infinity. So basically, this is an infinite world. So with this sign, so integral sign. So we have a name for them. So this elongated S and the ds are pair. Okay, they cannot survive one without the other. What does this mean? The meaning is we cut x-axis into infinite many pieces. We cut x-axis into infinite many pieces. So it's a pair. All right, then add them up. So that's the meaning of this. So that's one dimension. So this one and this one is a pair, makes one dimension. Then f of x is another dimension. So we see two values, right? We have the value on x-axis, multiply the value on y-axis. Let's see, this is f of x. Let's see, this is f of x. So we have this, the value of this, multiplied by, because we cut into infinite many pieces. Let's see, this is one piece. Right. The height multiplied by this will get this area of this triangle. Then the height of this multiplied by another piece of x, because we cut into infinite many pieces, each piece. We can use this, or maybe we use dx, right? So multiply, we get all this area. Then we add them up. Remember this sign, like this. Then we add them all up. But then because we cut into infinitely many pieces, so this becomes accurate. If we only cut into finite pieces, that's just approximation. We call Riemann sum. But because we're cutting infinitely many pieces, that becomes accurate. So that's the area and the graph area and all that. So it's a two-dimension value. So let's see this. So determine, so r x raised by r dx, right? This is a, so when we differentiate this, 1 over r plus 1, you see this is y, this is anti-differentiation, right? When we differentiate, let's say 3x squared, let's say when we differentiate x cubed, we get a 3x squared. So now we want to anti-differentiate. So how do we anti-differentiate this? We rewrite this one with plus 1 to the exponent. We add 1 to the exponent. We divide by the new exponent. Then we plus c. So we use this pair to represent the anti-differentiation. Right? We use this prime for ddx to represent the differentiation. We use this pair to represent the anti-differentiation or integration. Then we simplify. So 3 divided by 3, that's gone. So we get x cubed plus c. That's our, then we use f of x to represent that. So anti-differentiate, we get an original function. Right? So that's why this, the first one, what are we going to do? We're going to add 1 to r divided by r plus 1, then plus c. If we give a name, call this f of x. Right. The second one, we're going to do division. The second one equals to e to the kx divided by k plus c. Right, so we can write as 1 over k e to the kx plus c. And that's it. Make it easy. Okay, it's not that complicated. We're just doing backwards of the differentiation called anti-differentiation or integration. Before we multiply, we subtract. Now we divide, we add. Right? So we're just doing the backwards. Let's see these ones. right? So this one, let's see, equals to, well, x square root of 2, just square root of x is just x raised by half, right? So what are we going to do? We're going to add 1 divided by the new exponent. Then add c to it. Well, that's x square root of x, right? Because x raised by 1, just 1, x raised by 1, square root of x. Then divide by half plus 1, that's 3 halves. Well, this is a 3 layer. So divided by 3 halves is multiplied by 2/3, right? So we can pull this 2 in the numerator, and that's it. Or we can write as 2 over 3 x square root of x. Oh, of course, we need to add a c, right? We cannot forget about add a c to it. Let's see, how do we do this? Well, we have x raised by -2, right? Because 1 over x squared is x raised by -2. We plus 1 to this, so we divide by the new exponent, we add c. Well, that's x raised by -1 divided by -1, then plus c. Well, that's just 1 over x with negative, right? -1 can pull up front. X raised by -1, just 1 over x plus c. And that's it. So keep it simple. Just rewind the process of differentiation. Well, for logarithmic, remember when we have f of x equals to ln x, the derivative is 1 over x. Remember that? Right? So whenever we see 1 over some expression with x involved, so we can anti-differentiate, right? And we know that's going to be ln of this expression. Then, of course, if this is complicated and not as simple as x, we have to divide by, right? Because when we have x squared plus 1 before, what do we have to do? We divide this. So first, the derivative is 1 over x squared plus 1. Then we multiply. We have to do chain rule. The derivative of x squared plus 1, which is 2x, to get 2x divided by x squared plus 1. So we just have to do the opposite, right? We would get 1 over the, we would get ln of the expression in the denominator, then divided by the chain rule, divided by the derivative caused by the chain rule. So of course, we're going to add c to it. And why we need to put an absolute sign? Because the graph of ln x survives only for positive x value. So inside the log has to be positive, right? Because 2 raised by 1, let's see, 2 raised by 3 equals to 8. We can rewrite, let's do e. E raised by 3 equals to something. It will never be negative value, right? Will never be negative value or 0. So that's why we want to put an absolute sign here to enhance such expression cannot be negative. So the addition, the summation of two functions, right? If we anti-differentiate the sum of two functions, we can split to anti-differentiate each by each, one by one. If we have a scalar inside the anti-differentiation, we can pull outside, just like a differentiation. Well, let's see this one. Right. So this one is saying, let's anti-differentiate this. So dx and this is a pair, right? So we'll anti-differentiate one by one. So x raised by -3. So we're going to do x raised by -3 plus 1 divided by -3 plus 1 plus 7 e to the 5x divided by 5. Remember 5 is an m plus, well, 4x raised by -1, right? 4 times, when we differentiate, what's 1 over, well, let's do 4 times 1 over x, ln x, right? And we want to emphasize x to be positive plus c. So then let's simplify. -3 plus 1, -2, to put a negative sign up front. But x raised by -3 plus 1, -2, x raised by -2, it goes to the denominator. So 2x squared, right? -3 plus 1, -2, negative sign put up front. So I have 2 in the denominator. Then the numerator of x raised by -3 plus 1, which is x raised by -2. Well, x raised by -2 is 1 over x squared. Now, plus this one, 7 over 5 e to the 5x. Then plus 4 ln absolute sign of x, then plus a constant term. Okay, so to do 1 by 1. If sometimes we're given initial function, we can find c. Right? We can find c. So this saying find function f of x when the derivative is this and give us a point. So let's anti-differentiate. So f of x equals to x3 divided by 3. We add 1 to 2, then subtract 2x, then plus c. Now, this is saying when x is 1, y is 4 over 3. So 4 over 3 equals to 1 raised by 3 is 1/3. 1 times -2 is -2, then plus c. So c equals to 4 over 3 minus 1 over 3 plus 2. Well, 4 minus 1, 3 over 3 is 1, 1 plus 2, which is 3. So we get a specific function. So f of x equals to 1/3 of x cubed minus 2x plus 3. Right? So because how we know? Because we're given this 1 point, so we can solve for c. Okay, let's see this function. Let's see this example. A company's marginal cost. Remember marginal cost? Marginal means derivative, the rate of change. So given this, and we want to uncover to the cost function. Right? We do the same thing. We add 1 to 2, get 3, then we divide by 3. Then we add 1 to 1, get x squared, then we divide by 2, then e to x plus c. So the process is the same. Then we just plug in the value given, then we solve for c. Then we get the cost function as such. Then we can use the cost function to evaluate when x equals to 30 and 60. Right? So this is asking us to verify. So how do we verify? We just take a derivative of this side, right? If we take a derivative of this side, we reach this, that's verified. So this is the same thing, right? We just take a derivative of the other side, then to see if it equals to the inside. All right, we're gonna keep going for next